Yep.
All right, good morning, first period chemistry class. Dr. Harper here with a little bit on acid-base chemistry. I want to thank Rebecca Harper for helping me put this together. I want to just share with you a little bit about the different types of acids and bases, but I want to remind you too, this is going to be largely on you guys. Your textbook section on types of acids and bases is a little bit complex, but very, very good. It's very clear. I want to hit some of the high points related to that, though. We've got Arrhenius acids. They're the most simple type, okay, and probably the most practical in day-to-day chemistry life, okay? But an Arrhenius acid is a hydrogen ion producer. It will release hydrogen ions in aqueous solution, okay? An Arrhenius base is a hydroxide ion producer. It will release hydroxide ions in aqueous solution, okay? How about a quick example of those guys? Good old hydrochloric acid is a classic Arrhenius acid because in aqueous solution, it releases hydrogen ions. A classic Arrhenius base is good old sodium hydroxide, NaOH. It will release hydroxide ions in aqueous solution. All right, so they're pretty straightforward, those Arrhenius acids and bases. Our next category, and this is one we haven't talked about a lot through our distance learning as best we could. We haven't mentioned this a lot, but Bronsted-Lowry acids and bases. What are they? Well, a Bronsted-Lowry acid is a hydrogen ion donor, okay? A Bronsted-Lowry base is a hydrogen ion acceptor. It will receive hydrogen ions into its compound, or in forming a compound, okay? How about a quick example of one of those guys? All right, our good friend ammonia, NH3 here. It is a Bronsted-Lowry base because ammonia will accept a hydrogen ion. Water. Huh? What do you mean? Water is an acid? Yes, it is a Bronsted-Lowry acid because it will serve as a hydrogen ion donor, okay? When that occurs, we produce the ammonium ion, NH4, and we have hydroxide ion released as well, okay? So that's a good example of a Bronsted-Lowry acid, water, and base, ammonia, okay? And then the final category, Gilbert-Lewis, somebody had to make it even more complicated, right? A Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. What's this all about? Well, we did a little bit of that with our formation of Lewis dot structures. You remember those guys? Woo! All right, here's a nice example of Lewis acid and bases. We've got hydrogen ions that may have been released in aqueous solution, right? The hydrogen ion is a Lewis acid because it's an electron pair acceptor, potentially, okay? Now I've drawn the structure of it. We could have just said H2O, but here's water. Look at these unshared electron pairs in the Lewis structure. It's a Lewis base because it's an electron pair donor. That electron pair could be used to form a covalent bond with the hydrogen ion, forming something we call the hydronium ion, H3O. You're kidding me. Yes, that's what it is, all right? So that is an example of Lewis acids and bases. Go over that in your book. Check it out. Play with the examples in the book and try to familiarize yourself with those three categories of acid-base types, okay? Now, I want to do a little demo, and I'm going to have to move around a little bit, so be patient with us as we jump around, but maybe it'll make this business of acid-base chemistry mean a little bit more for you, okay? So what we're going to do, we're going to take some milk of magnesia. Ooh, it looks really delicious. And we're going to put about 20 mils. This is bucket chemistry. It could be 19 mils. It could be 21 mils. But we're going to put about 20 mils milliliters that is, in this beaker that has a stir bar already in it. And this is a 1 liter beaker, 1,000 ml beaker, okay? All right. What is milk of magnesia anyway? Well, I just want to make sure I have enough, right? It's bucket chemistry, all right? What is milk of magnesia? Well, it's something you can get at the drugstore over the counter. It's magnesium hydroxide suspended, because it's not extremely soluble, it's only a little bit soluble, and it's suspended more than it is solubilized in water, okay? And its purpose is an antacid. Your stomach produces hydrochloric acid. It's critical to the digestion process, but sometimes it produces too much, okay? And when that bumps up against your lower esophagus, you get heartburn, right? It's literally digesting, that HCl is literally digesting parts of your esophageal tissue. Not a good thing. But maybe milk of magnesia could come to the rescue and neutralize those H+ ions that HCl released in your belly. Okay? So let's check it out. Now, we want to bring this up to about 800 mils with distilled water. So we're going to put a little distilled water in here. Ooh, nice, creamy, milky. All right. All right. Let's get up there around 800 mils. Okay. And I want to cool it down just with some ice cubes. And the reason is, you remember this from your solubility work, that lower temperature usually means less solubility. We don't want that magnesium hydroxide to be too soluble. Here's magnesium hydroxide formula, and it releases these hydroxide ions into that solution, okay? What could that OH do? It could say, hey, I can scarf up those hydrogen ions and basically reform water and stop that acid burn, right? Okay, so that's the whole idea. Let's see if we can get it stirring. I want to create a little vortex here. Oh, that's nice. Come on, baby. I think we're getting there. Yep. All right, so just to keep it, because remember, magnesium hydroxide is only slightly soluble. And I think we're just jumping now, not... Come on. Give us a nice steady spin. I think that's pretty good. We don't want to overdo it. All right, so this is universal indicator. It indicates pH. You've done pH, right? You understand what that is. pH is the negative log of the hydrogen ion concentration. It's not just a number. But when that number is below 7, we have an acidic condition, and above 7, we have a basic condition, right? Universal, all it is a color change to show you the pH. Highly acid pHs with this indicator would be a red color. Highly basic would be deep purple, okay, right? And these various colors in between would be along the pH scale. So we're going to put some of this indicator in this solution. What do you think it ought to be color-wise if basic is dark blue to violet? Well, that's magnesium hydroxide in there. What do you think? What's it releasing in there? We're going to put a generous helping here. Oh, deep purple. How about that? Isn't that cool? That must mean it's extremely basic, right, good people? Let's put a little bit more indicator in there. Isn't that pretty? All right. So now the indicator is telling us we're very basic, right? Okay. So what's mostly released? Hydroxide ions. They're predominating. They're the king, right? Right now in that suspension, in that solution. But guess what I have on hand here? Some 3 molar HCl, 3 molar hydrochloric acid. All right? You know what 3 molar is. Y'all did molarity. That's 3 moles of HCl for each liter of water, right? Or solution. You remember that? Hope so. Well, 3 molar is pretty stout HCl. And we're going to check this out. Let's say your stomach now, you just ate a couple of burritos and you cranked out a bunch of acid. Whoa, isn't that cool? And that's kind of close to red. We have overwhelmed the magnesium hydroxide. We've got more H plus ions released in there. But watch carefully on the, what might happen? Those H pluses are saying, oh, OH minus, I'll join you and form water. Okay, I'll join you and form water. Oh, now I'm neutral. Holy mackerel. I'm neutral, but wait a minute. If I form more water, maybe more hydroxide ions can be released into solution. Let's hope so. Come on, Seabiscuit. Is that stronger than 3 molar HCl? Nope, wait, what's this? Am I going back to deeper blue and approaching purple? But I could eventually, now I'm back to basic, aren't I? Okay? I've allowed more hydroxide ions to go into solution because it neutralized those H pluses by joining up with them and forming more water, more H2Os. That's a neutralization reaction. That's cool. What if I said I want to overwhelm you again? Look at that. Once again, I've overridden the system with hydrogen ions. OH is now the loser, right? OH is now the loser. Oh, but wait! How about that? It's returning to neutrality. Now it's trying to go back to basic because once I form more water, I scarfed up those H pluses, right? Then I return to having a greater opportunity for more hydroxide ions to go into solution. And we could keep doing this and keep doing this to eventually we override the Haley's milk of magnesia. We'll just keep going, and you can't beat me now because I'm going to just fire the hydrogen ions to you till you just can't stand it any longer. And you will not return to a basic condition because there's no more hydroxide to use in our neutralization. Okay? So at that point, we're not going to be able to go back. We're going to stay acidic. In fact, I've got to neutralize this with some sodium bicarbonate before I can get rid of it. Signing off, but remember, check out those Arrhenius, Bronsted-Lowry, and Lewis acids and bases, as well as the previous stuff on pH, etc. What? Oh, I can't stand it. We've got to keep this, we've got to go back to acid. If I have to, I will get my HCl and keep going. How are we doing on time?
13:24.
All right, well, we're all right. Let's go ahead. I want to prove to these guys that I can eventually overwhelm my magnesium hydroxide. Have you been overwhelmed yet? I think he's overwhelmed at this point. In fact, it should become of greater clarity, clearer with the red color. And I think you can see that. Do it. Bucket chemistry, good guys. All right, so check this out. Check your book out. Early next week, we're going to wrap this business of acids and bases up. Okay? Have a good day. Hang tough.